Okay. All right. Problem 3 uses a very similar circuit to this one. Okay. In problem 4. Problem 4, you have 3 inputs, V0, V1, and V2. And I basically give you sort of a truth table of options here, like that, you know, or 0, 0, like, you know what I mean, 0, 0, 1, like that. All right, those are voltages. And the thing is, this may be something people aren't as familiar with. But when I have this here, basically what I'm saying is, imagine I got a voltage source here, V1, or V2, like that. Okay, so imagine I got voltage sources like that. Okay, how should I approach this problem? What's the best way to try something like
Superposition.
That? Superposition. All right, to do superposition like this. All right, and so what I want to do is do superposition and then basically use the golden rules as I walk through this. Right, so I'm going to do V1. So what I want to find is, I want to find V out, just like I have there in the homework. Let's say A1 V1 plus A2 V2. I want to figure out what A1 and A2 are. Okay. And to make life a little bit easier here, I'm going to say that R1 equals R2 equals R3 equals R4 equals R. So they're all the same value. Okay. That is actually, this particular circuit, which is called a difference amplifier, is most typically done that way. All right. So I've got all those resistors equal to each other. And I want to figure out what's A1 and A2. So I got to do superposition to do that. Okay, that's a problem we're going to try. All right, very similar to what I have in problem 4. Okay, so all right, let's do that. So how do I approach that? How do I do the superposition then here? Turn off. Well, let's turn off V2 first. Okay, so let's say V2 is off. So if it's off, it's equal to 0, right? So it's a short circuit. So how can I simplify the circuit down if V2 is off? So if V2 is off, it's 0 volts, right? So what do I do with the V2 source? I short it, right? So that means it's shorted to ground. So the circuit would look like this. Here's V1. Here is, I gotta be careful I give myself enough room here.
Are those V1, V0, V1, V2 supposed to be like a matrix or something?
No, this is for problem 4. Okay. We'll come back and talk about that separately, okay? It's just, let's focus on this circuit right here, okay? So V1 and V2, we're going to turn V2 off. So the circuit's going to be, here's V1. Here's R. I was going to call them R because I said they're all the same value. Here's R. Okay. Now, this is my ground. Here's my V out. What's going on at the plus terminal? If V2 is off, V2 is a short circuit, right? So what's that mean about this resistor here, R2?
It's in parallel with R4.
It's in parallel with R4, right? So basically I've got, since they're all the same value, I say I've got R and R here, like that. All right, it's down low enough that it doesn't want me to draw any lower.
This is like the trickiest part of this whole
Well, hopefully nothing I did right up to that point was tricky. Maybe it is. The only thing that's tricky is there's a triangle in the middle of this, right? But basically up to this point, this is all circuit. Now the next step is the tricky part. The next step is now where the OpAmp comes in. What is the next step? What do I have to do to analyze this guy?
Nodal.
I got to go to my golden rules. I'm going to use Nodal. Somebody said Nodal. I'm going to use Nodal to do my analysis, but now is the point where I do my golden rule idea, right? This golden rule idea basically is, what are the two rules that we need to apply?
V plus equals V minus.
V plus equals V minus.
I plus equals I minus equals 0.
I plus equals I minus equals 0. All right. So looking at this, from those two rules, how much current goes through these two resistors here and here?
0.
What's V plus?
It'll be 0 because there's no voltage drop across the resistors. That means it's the same voltage as ground.
Totally correct. Yes. V plus equals V minus equals 0. That's not always true that V plus and V minus are 0. Okay. In this case, the order is I plus is 0. So V plus is 0. So V minus is 0. All right. That order matters, right? So basically what I said is I plus is 0. Right. That means that V plus, which is equal to I plus times R in parallel with R, is 0. And by this rule, they're both equal to 0. Okay. So that basically says that now I can do my analysis on this guy with nodal analysis. Okay. So you can think of this, if you wanted to do it this way, I guess what you could even get rid of the OpAmp at this point if you wanted to, if you like it better that way, and just say I got V1 R ground and another R here, and here's V out. If you feel better with that, you could do that, right? I don't like doing it that way, but that, the reason I don't like doing it that way, and I'm not, I wouldn't do it that way, because I want to be mindful of a couple of things here. Here's the resistor. Here's the resistor. What I would say is, if you want to, you can just think of this as that being grounded, right? That may be a simpler way for you to think through this particular problem. All right, here's V out, okay? And specifically, I guess I'm gonna call this V out V1, right? Because this is really just the component that is coming from the V1 source. You gotta be careful about that. So to do this, I gotta do nodal analysis, all right? Now, you can go online and say, well, there's a formula for this guy. This is an inverting amplifier. It's a common circuit, right? So I could easily go to Wikipedia and find, the 10 most common op-amp circuits, and this guy would be there, right? But I saw at least one person, Eli, put the KCL in the wrong way into Discord. So let's make sure we're following that, right? So what I'm saying is I got a current going this way, and I got a current going this way. Again, that's the way I write my KCLs for this node, right? So at the V minus node, so I'll say at the V minus node, what's my KCL here?
IC equals.
What's your IC?
I mean, I minus, not IC. Not that. Just that first, the current going through V1 and R is I minus, right?
So I minus, yeah, good question. I minus is here. I minus is the current going into the op-amp. All right, let me draw it with capital.
Okay.
I minus is the current into the minus terminal of the op-amp. So at that node, I have V1 minus 0 over R. That's a current going into that node, right? And then I have two currents coming out. One of them is I minus. And one of them is what? What's the current in this resistor here? That's, okay, 0 is the voltage at the plus terminal. Minus V out is the voltage at the negative terminal, or at the minus terminal, okay, over R. This guy is 0. And if I rearrange this, I'm going to find out that V out equals, anybody know?
V1.
Negative V1. right? V out equals negative V1. And again, I was calling this V out V1, so I should be careful. V out.
Why is V1 positive? Like, if you're doing, I don't know, I always get confused when you do that. Like, is it minus V1 or plus V1?
I know why she does it, because I do it the same way as her.
So okay, there's the question that Kate is asking, I think here is, this gets into the way that I do KCLs, the way I learned it, right? So I just define my current directions and I define the voltages across the resistors. And the way I think about it, if this is I1 and this is I2, by definition, the voltage, if I call this V, I shouldn't call it V1, we've already got a V1, don't we? I'll call this VA and VB. Just by definition, VA, which is V1 minus 0, is equal to, by Ohm's law, I1 times R. And VB is equal to 0, the voltage of the plus terminal of it, minus V out. And that's equal to I2 times R, like that. That's my way of doing it. And then I do currents in equal currents out.
So it doesn't matter if the plus and minus is first on that voltage source, or just because that's the one going.
So what matters is that I write down my Ohm's law consistent with the passive sign convention, and that I write my KCL consistent with the directions of my currents. Right? If, let's say, I don't like doing it the way that you guys do it, for a reason. You guys, I think the way you learned it in 2111, typically, it's not wrong. It's just a different way of doing it. It's the way Zybooks does it. Is you say everything going out. That gives you a consistent set of equations. And I talked about this when I first talked about nodal, right? Basically, if you do it this way, what you say is, all right, the actual current in this branch may be the opposite direction of what I drew here. You're going to end up, the assumption that you're making here, every time you write your KCL, you're making the assumption that all the voltages all have that polarity. The reason I never like this is if I have this set up, let's put a resistor here. The reason I never like this is because then if I do the KCL at this node, this picture bothers the crap out of me because I know the current goes one direction in this middle resistor, not two ways, right? It can't, but what's going to happen is this guy is going to be 1 amp and this guy is going to be minus 1 amp. So they actually are the same thing. That just, I don't like that. I never have. The way you guys are doing it just kind of covers up it tries to get the passive sign convention, Ohm's law, and KCL current directions all without you thinking about it. Which is, maybe good, right? Maybe good, maybe bad. My take on it is it's not good. But it's out there and it's what you know. So if you want to do it that way, you could. So if you wanted to solve that problem, you can say, okay, well, I'm going to say those currents are going this way. So if you did it your way, you'll get the same answer. So if you did it this way, and this is R, and this is R, then you always have to say, okay, well, I'm going to have 0 minus V1 over R plus what? 0 minus V out over R. And then I minus is this way. So plus I minus equals 0. That's the same equation. Right? If you want to look at it that way.
If your following his method where you're following the actual current, if you just do like a KVL at the same time, it'll produce his equation. So
Yeah.
if you did negative V1 plus V of R,
Yeah.
and the node is V minus, you rearrange,
Yeah.
and you get what you get. So if that confuses you, can just do that proportion separately.
Right.
Okay, thank you.
Wait, so,
Yeah.
if the voltage source, like the polarity was flipped, or it can't be because.
If the polarity of V1 was flipped,
Yeah.
it wouldn't necessarily change anything. Let's work this problem through. So I'll do my next one your way. All right. So V out V1 is minus V1. All right. We only did half the problem. We've only done half the problem so far.
So we originally had these resistors labeled R1 and R3, but so now we're just continuing the problem, assuming that they have equal resistance, and so we have no gain.
So, well, it depends. I gotta be careful with that. So I set them all equal to R. So they're all equal to each other.
All right.
I'm gonna be careful about the word no gain. It's not that there's no gain.
Right. Well, I mean, for the last
What I would
circuit,
say
that's
is
what
this
we're done
guy's got magnitude wise, and this is a good time to talk this through. Okay, let's say I had just this circuit right here.
Mhm.
What is the gain there from input to output, V1 to output? What's the gain?
-1.
-1. That's not no gain.
Right.
What I would say is, I don't know what I would call it, but the term that we typically use, the magnitude of that gain. So if I call that gain A, that gain is -1. V out over V in is -1.
Mhm.
Magnitude wise, that guy has what I call unity gain. All right. We are careful to use the term unity gain. I think I don't know, that's what I learned. But the reason I think we always do that is because of the fact that no gain kind of implies 0 as the value, right? And that's
Mhm.
not, in other words, you're correct, Matthew, in that, what you're going to have is output and input are the same magnitude. So it's not getting bigger or smaller, right? That is kind of no gain. But I think the term no tends to imply to people that like there's nothing there, right? So we use the term unity gain.
All right.
Now, this is the question I saw come up a couple of times already in the chat or in Discord, right? When I say the gain is -1 like this, its magnitude is 1. What is the angle of the number -1?
Would it be 180?
180 degrees. Okay, 180 degrees. And if you just simply tried that by going e to the j 180, and you went all Yahoo style on that, you would see that that's equal to -1, right? So in other words, cosine 180 plus j sine 180 becomes -1, right? So the angle of a real number has an angle. It's either 0 or 180. And think about that till, when you were a kid and you learned the number line, right? The number line, positive numbers were going this way, negative numbers were going that way, right? So it's the opposite direction, right? That's a 180-degree swing, right? That's the easiest way to think about that. Okay, we're still only halfway through. All right. Questions about this piece? Because this is one that has come up already many times in the Discord.
I do have like a small question that you said that it mattered the order that we're calculating, like V plus equals V minus. Like, I understand where you're going with that.
All right, well, let's do it. Let's do the other part of the problem,
Okay.
and I'll see if you can figure out the order. All right, so what we've done is we set V2 off, and we found that V out from V1 is equal to -V1. So the other thing I got to do is I got to find V out from V2. Okay, so here's our circuit, our original circuit here. So if I turn off V1 and turn turn off V1, turn on V2, what do I do with the circuit then? So what do I do to the circuit if V2 is on and V1 is off? Short circuit V1. All right, so that's going to turn this guy into, let me erase all this. Okay. All right. Now, okay. Oh man. V1 is shorted. So here's R. V plus over here. Here's R. And then there was a V2 over here. Okay. Oops, not directly. Here's R, like that. So where do I go with this guy? I want to find, so my job is to find V out V2, right? So what's the output that's coming from just the V2 source? What is that equal to? Well, so so at this point here, I could do some simplifications if I wanted to. One thing we do nodal analysis here, right? I got a node to solve for here, V plus, right? I could solve for that node. I don't want to do nodal analysis. I don't like it. Looking at this, how much current, what is I plus when I apply my golden rule here?
0.
0. All right, so my nodal analysis gets super simple then, doesn't it? So because I plus is 0, I know that V plus is what? No? So V plus is equal to V minus, that is true, right? But looking at this circuit right here, what do I see about the fact that I plus is 0 means that this current equals this current. So I got a voltage divider, right?
Yeah.
Now I could have done that by just doing nodal analysis and seeing, well, whatever current I have here equals the current here plus the current here. But this current is 0, I plus. So I got a voltage divider. So I have the V plus equals V2 divided by R1 plus R2 times, and I gotta be careful because I'm just calling them R plus R times R. Right, the current in that loop is V2 divided by R plus R. That the voltage here, V plus, just to be clear about that, V plus is that voltage. Is that. Okay. Questions about that? Now I apply the golden rule. That's V minus. So in V plus and V minus are always equal, but they're not always equal to 0. All right. So in this case, I see V plus and V minus are the same, and they're equal to, if I do the math on this, Tone already had it there, it's V2 over 2, right? Because those two resistors are the same value, it's going to be V2 over 2.
I minus is equal to 0 too, right?
I minus is equal to 0 as well. Yeah.
Oh, but never mind.
So now the question becomes, how do I figure out what the gain is? I'm only halfway there. I want to figure out V out V2. So what can I do up here at the top terminal? I can do nodal analysis again. All right. So if you want to do nodal analysis, let's do it your way. All right. So let's say current goes out, current goes out, current goes out. All right. We'll do it that way. All right. So help me out. If I do it that way, 0 equals the sum of all those currents going out. So how would I write the current going into the resistor that direction? How do I? So
V minus minus 0 over R.
Yep, V minus 0 over R. That's the current coming out of there, right? Then what about, then I have I minus is the current here, right?
Why do we assume that on that voltage, that the voltage with that's like right next to I minus is 0? Because it just has a resistor and no voltage value?
What? No. What are you talking about?
So that V minus minus 0.
You talking about
R,
this resistor right here?
that's the first one we're doing.
This is,
right?
yeah, that's this one, yeah. So let's give them names. All right, let's give these currents names. This is I1, this is I2, and this guy over here is I minus. So I'm going to say 0 equals I1 plus I2 plus I minus. Okay, I minus is just 0. Right, just always is. OpAmp's built that way. Okay. All right, what's I1? I1 is the current in the resistor that's connected to ground. So that's V minus, so V minus minus 0 over R. What is I2?
V minus V out.
V minus minus V out 2, or V out V2, I was calling it. V out V2.
I thought
over-
V minus was entering the negative terminal of R for I1.
So I'm trying to write it the way a lot of you guys write this. I'm basically, so I'm going to make the assumption all the currents leave the node. That's basically the way I've written this out. If I'm making the assumption all the currents leave the node, the implicit assumption in that usually is that the voltage are going plus minus like that.
All right.
So I'm doing it different than the way I would normally do it, which is definitely the case. I'm doing it the way that I think like probably most of you guys do it. Not everybody, but a lot of people do it that way. Okay. Now, in this particular case, what I can do is V minus and V plus are the same, so I put in V2 over 2. All right. If I put in V2 over 2, right now, just with this expression right now, I can see the R's go away, right? I can multiply both sides by R. So I have V minus, which we said, well, let me just get to V minus minus V out 2, V out V2. V minus is V2 over 2. Like that. V out V2 is equal to V2 over 2.
Isn't V out in that case just equal to 2 times V minus? You multiply everything.
Yeah, but we have a value for V minus in terms of this guy. And actually,
So V out would be equal to V2.
yeah, sorry, what did I do wrong here?
Why isn't it 2?
There's 2 V minuses.
Because I think
There's 2 V minuses. Thank
Yeah.
you. Thank you. That's what I did wrong. Yeah. So this guy, yeah, it should be 2 V minus. All right. So if you, again, to get from here to here, there's 2 V minuses. Yeah, my answer was not looking right. So this is just simply V2 here, right? So this guy is that. V out V2 is V2. Okay. That means that my total answer here, so V out V1 was minus V1. V out V2 was V2. So the total response here in this particular case is that V out is equal to, according to this, A1 is my minus 1. A2 is apparently 1. So it's V2 minus V1. That's why we call it a difference amplifier. It subtracts 2 voltages. Okay. And that is actually a pretty useful circuit in a lot of cases. All right. We use that a lot to shift signals up and down, for instance. Right. It's a pretty common thing to try to do. Okay. This is one I have built many times for real applications. All right. Now, this is not exactly the problem that you have there let me jump down all the way here. In the homework, very similar. You have this guy. Okay. And then over here is basically a set of 3 resistors. Not drawing this very cleanly. All right, what you have is resistor here, resistor here, resistor here, and you have V0, V1, V2. Do the same basic approach. Okay. So basically turn off V1 and V2, turn on V0, right? And what do you get? And you do a nodal analysis in each of those cases. Okay. The thing to note when you do the superposition, this guy here is going to be at ground, right? V minus is going to be at ground. V minus is going to be 0. So that means that when I'm doing the superposition, what I do with those other two resistors becomes pretty simple. The circuit analysis gets really simple in this case if you understand what to do with the superposition. All right.
I didn't catch that. You said V minus is at ground?
V minus is at 0 volts. So why? So V minus is at ground in this circuit. Doesn't matter, right? Because V plus is at ground, right?
Okay, I see what you
V plus is at ground.
Yeah,
Yeah.
okay.
And then, you know, I can do nodal analysis. I mean, if you wanted to, you could do nodal analysis without doing superposition pretty easily. And just say this current, this current, this current equals that current. You could do superposition without doing nodal analysis. Or you could do nodal analysis without doing superposition if you wanted to.
Is there anything wrong with doing that? Because that's what I did to answer this last night.
Nothing wrong with that at all.
What would that
Yeah.
current leaving the node that connects all three be equal to if there's no, like, there's no element? There's nothing for me to play with on that branch. You know what I'm saying?
There is a branch, right? Whatever current I have here goes here. And remember inside here, there's some sort of a source,
Okay, yeah.
right? That is one thing to bear in mind, is the fact that there is current can go in there. You can go into that. It can go into the output side of the triangle, but it can't go on the input side of the triangle. Yeah, and nodal will be perfectly fine for this guy. Now this becomes what we call a summing amplifier, and it's the name that we sometimes give to this guy. Basically what I get is, if you do this right, let's say all of these resistors, if they have the right value, the output could be minus V2, minus V1, minus V0, right? The way I set this up for you guys, the values, what you should see is I give you this table, I think it's V0, I can't remember the order, V0, V1, V2, like that. And I basically say, well, what happens as we change these values? So imagine V1, V2, V1, and V0 were all 0. What's the output going to be? What if it will be 0? Yeah, that's the easy one, right? 0, 0, 1, what's it become? Well, then you got to use the math for that. Then if it's 0, 1, 0, what does it get? Yeah. And what you...
Coincidence that you're counting up like in binary?
Well, I call this guy as a digital analog converter, right? So basically, if 0 volts is a 0 and 1 volt is a 1, if basically I had a 3-bit digital value, here's how I can convert that 3-bit digital value to an analog value, right? So this is a D-Day converter or a DAC, right? That's what. And what you'll see is as you walk through my table, this guy will be the smallest number. This guy is an equal amount bigger, an equal amount bigger, equal amount bigger, until it gets up to 3 volts, I think, in this case, at the high end. Okay, so that's basic way that people make what we call a DAC. Okay. All right. One other question then, sort of similar. Okay, so you got a problem in problem 3 of the homework, where you have to do some nodal analysis. In that particular case, the circuit's a little bit more complicated, but the thing with your nodal analysis, basically to remember, is this terminal right here, this V minus terminal, is always going to be set by something else in the circuit, okay? So in the particular case of, let me just jump straight to, I'll just go straight away to homework 7. Yeah, right? The thing to notice about this circuit, this is just going to be nodal analysis at 2 nodes, right? There's going to be a nodal analysis at this node right here between R1 and R2. And then there's going to be a nodal analysis that I do right here. Okay. What is the minus terminal? This? Well, so in this particular case, I'm going to do nodal analysis, right? That's what we're going to try to do to try to figure out a relationship between V in and V out. Okay. So one thing about my golden rules, and maybe this is the key thing about the process, is I always have to find a way to be able to set the plus and minus terminal to some fixed value. In any of these problems, V minus and V plus are going to be set to some fixed value always, right? So in this case, which terminal do I look at to see that it's fixed? So if I look at the minus terminal here, the minus terminal is always at what value? V out. That means that V plus is always at V out. V plus equals V minus. V minus is V out. So this node right here is V out. Now it's not connected directly to V out, but it is forced to be at V out.
Those
Okay.
2 nodes are confusing me. Like right next to V out, what is it? Those 2 nodes connecting?
These?
Yeah. It's the same node, right?
It's the same node, yeah. It's just the picture was drawn so that they don't align with each other.
Okay.
Right. Your nodal analysis, you do a nodal analysis here between R1 and R2, and then you do one at the V plus. So in this case, what you know is that this plus terminal is at V out. Okay.
Wait, you say the node equals to V out?
So yeah, so the critical thing here is V minus. What do we always know? V minus and V plus are the same. Somehow, some way, there's got to be a way for me to fix V plus or V minus. So when I'm applying the golden rules, maybe the way to think about this, I don't know if I write this out. The way I would think about applying this, if I tried to write out an idea for how to approach it. V plus or V minus should somehow be set by some combination of sources in the circuit, where those sources could be, one of them could be V out. V out is a source, right? It's set by some combination of those guys, right? So, or V in, right? There could be 4 sources in the circuit, but somehow one of the 2 is set by some combination of sources and the other one is equal to it by the golden rule. And the other one is equal to it by the golden rule. V plus equals V minus, right? That's probably the way to think about that. One of them should be settable. The thing to think about is maybe that V out is a source. So in this case, V out is the source. So that's good. V out is equal to V minus. So V minus is the one that's set by sources, and then V plus is set by the golden rule. So look for the one that you can set by sources, and then look for the one that you can set by the golden rule. Okay. That's probably the way to think it through.
Professor, for V plus and V minus, how do you know where the ground is? So, like for V minus here, is the ground the same ground for V out?
Yeah, so you always have to have the same ground. All circuits have to have the same 0 reference point. We could probably do a whole conversation about ground, but ground is our reference node. In any circuit, in order for current to flow, there better be a connection between everything, which means that they all have the same ground.
And since we only care about steady, those capacitors are acting like open circuits, right?
you are told that you have a 10 kilohertz voltage source with this phasor. So then you plug in the impedance equation.
Okay.
Would you just do nodal and then take the value from, since that the V plus?
Yeah, so if you do your nodal analysis in this case, you're going to get a relationship between V in and V out, right? And so you would plug in my V in as 3 angle 20, and you would get a particular V out. Now the thing is, this is a good, other than the fact there's an op-amp in here, this is great practice for the exam, because the kind of thing on the exam I would probably do is say, okay, well, I've got a 10 kilohertz voltage source, and there's a capacitor, 1 nanofarad, capacitor, 1 nanofarad. You tell me the impedance, right? It may not just be negative J4 or whatever, right? Knowing that it's 10 kilohertz, you should know how to calculate the impedance. Right.
You mentioned earlier that they all have to have the same ground. How would they not have the same ground? That doesn't make any sense. Like,
Well, like I said, we could go on a whole tangent about ground. I'd be happy to take that offline. There is such a thing So ground, more generally, we talk about references. So a circuit has to have a reference point, my 0 voltage point. So in that sense, I can have different reference points, possibly. That is not a good idea typically. Sometimes it happens.
So are we allowed with the ground?
You'll never have let me just to wrap on that. You'll never have a circuit with different grounds in here, just to be clear.
Gotcha.
Yeah.
So are we allowed to, with like the 2 ground nodes, so like from the negative terminal of V in as well as off of capacitor 2, could we potentially connect those with a wire and just say that was the reference node? Or no?
Which one?
From negative terminal V in, the ground on V in and the ground on capacitor 2, could we just connect those together as the reference node?
Yeah. So anything with, so this is okay. So good question there. So anytime I've got different points connected to ground, the implication is that all these guys are connected to each other like that.
Okay.
Yeah, it's a shorthand way of saying if it's grounded, we often don't draw that whole wire. We don't have to draw that whole wire, right? We just basically are talking about where that guy is connected to.
Right. I was just making sure you could actually do that.
You can.
Okay.
Yeah, because they're all at the same voltage, right? So that's totally fine. And that is how a real circuit would be constructed, right? Is it would have it that way. I always say mesh analysis isn't that common, and part of the reason why, actually. I mean, so once I draw circuits like this, the meshes become probably a little bit less clear, right? But these points are all connected to each other.
Is V plus here the voltage across capacitor C2?
So V plus by definition is always the node voltage with respect to ground at the plus terminal of the op amp. So this is V plus right here, right? And this voltage right here is V minus. So V plus and V minus are node voltages. That answer your question, Ibrahim?
Yes, thank you.
Okay. All right. So the thing to remember is there's 2 nodes here, right, that you'll need to worry about. One is this one. One is this one. All right. So you got to, so this one here becomes pretty easy, but the thing is, like, it looks like these guys are sort of in series, right? They are kind of in series because the same current flows through them. But there's a weird factor here, which is the fact that this is a fixed voltage. All right, this is a fixed voltage. What is the value of the voltage right here? It's V out. All right. So make sure you do a KCL here and a KCL here. All right.
Oh, it's V out because V plus is V out.
Mm-hmm.
Okay, I see.
Right. in that sense, it's like, because this point's V out as well, right? All right. The important thing is, make sure that what you can do is that you can, in any of these problems, you can identify what is the voltage at V plus and V minus, and then just usually it's nodal analysis from that point forward. Okay.
There was like something weird that the TA tried to explain through.
For which part?
It was like part one in the home, like the first problem in the homework when I couldn't understand why the phase angle, it seemed good.
All right. So it's with the DC part thing. All right. Anyway, let me go with one other kind of example here. So let's say I had this guy here. All right. Oh boy, now it's got to go through its whole. Okay. All right. Let's say I got this circuit here. And let's say I do the same thing like I did in the homework, which really threw you guys for a loop. I say, what happens if Vn equals 1 plus 2 cosine, I picked a number in my MATLAB, omega t plus 30 plus 0 degrees, make it easier. Like that. And omega is a number. Omega is, I picked a number in my MATLAB. What, I don't want to go out of this. Let's say omega was 100. Like that. Okay. If I have first of all, those are two sine waves at two different frequencies. Okay, that's the first thing to notice about that. 1 plus 2 cosine omega t is two sine waves at two different frequencies. All right? What do I mean when I say that looks like there's only one sine wave? And some of you guys would say there's no sine waves. There's a cosine wave and a constant, right? Cosines and sines are the same. Somehow I know sine and cosine I can shift 90 degrees one way or the other, and they can. I use the term sine wave to apply both cosine and sine. That's pretty common. Why is 1? Why am I also saying 1 is a sinusoidal waveform? The DC voltage. Okay. What is the frequency of a DC voltage? 0 hertz. 0 hertz. It doesn't vary. So if I think about it that way, if I had I like to think of it this way, 1 cosine omega t, if omega is equal to 0, what's this equal to? 1.
Just 1.
Yeah. Right? Basically, if you think about the number 1, if I plotted it versus time, right, it's always constant, right? This guy is basically, he never repeats on me. In other words, he's always the same value. He doesn't vary and then come back to the same point. This guy has an infinite period because he's the same value everywhere, right? Which means his frequency is 0. Okay. So this guy here is an omega equal to 0 term. This guy here is an omega equal to 100 radian per second term, apparently. Okay. So the thing that I think then bothers people with that, I think, is to say, well, I can think of this Vn then as two different voltage sources in series with each other. One of them is 1, and the other one is 2 cosine omega t, like that. And then this type of problem, not with an op-amp, but this type of problem is very likely to be on the exam, where I have superposition with sources at different frequencies. We had a problem like that in the homework, right? I like this problem because the trick to it is I can't analyze with both of them at once and use impedance. It doesn't work, right? If I'm going to use impedance, the implication is I look at one frequency, then I move to the next frequency, okay? So let's do so this guy here is Vn. And the way I look at this is, if I did KVL around this loop, that KVL would be the same function I gave you, all right? KVL around that loop is the same thing. So basically adding two voltages together right, is superposition. It's, you know, all that I can replace that V in with just those two sources and do superposition. Okay. Now, let's do this for DC, for the omega equal to 0 term. So in this case, I gave you C, L, R1, and R2. All right. So what is, so at DC, so omega equal to 0, the impedance of the capacitor as a function of frequency is what? Well, as a function of frequency, what is Z sub C?
1 over J omega C.
1 over J omega C. And ZL is what?
J omega L.
J omega L. Okay. If I plug in omega equal to 0, 1 over 0 is infinite. And this guy is what? 0. If I have a circuit with 0 impedance, that's like a component of a circuit with 0 impedance. It's like a resistor with 0 resistance. So this is a what? It's a short
circuit.
Yeah. And this guy is what? An open.
Open.
Yeah, if I have infinite impedance, I have an open circuit. Okay. So what that says is, you know, at DC, the capacitor does what in my circuit? Well, it just disappears, right? Goes away. That branch is gone. The L, what's it do? Well, it shorts out. Okay, when it shorts out, it just disappears as well, I guess, except it becomes a short in that case. So what I have is basically this. Here's R1. Here's R2. Like that. And here's V out. Like that, right? And I was calling this, I guess this is just 1 volt there. So I'll say V out DC. Okay. Now, so what did I do? I just simplified that circuit down, right? Because L is a short, C is an open. That circuit we've seen before. If you didn't remember that, so at this point, what do I do? V plus equals V minus. I said that's my golden rule. That's always true. The other thing I said was also one of those two terminal voltages can be set somehow by the circuit. In this case, which one is it that I can look at and say it's definitely set by the circuit? The circuit's pinning it at some point.
V plus.
V plus. V plus is pinning the plus terminal, or the ground. V plus, the plus terminal is pinned to ground, right? So it's stuck there at that particular value. And then at the other node, I do my work. Right, that's typically how we do it. One of the nodes is set by the circuit, and then the rest of them I have to do some nodal analysis or something like that. Okay. Now, in this case, if you go through that math, what you're going to find out is that V out DC is minus R2 over R1 times 1. Right. Now, I know that because this is a pretty common circuit. When I have two resistors like this is my inverting amplifier, there's a formula for that, minus R2 over R1, right? So, but if I didn't know that, I would just do nodal analysis right here, right? And I'd be able to solve it. So when I ask you to put this into, so let's say R2 was equal to 2 kilo ohms and R1 was equal to 1 kilo ohm, okay? That would make this guy -2, okay? So in MATLAB online and Canvas, I ask you to put that in, right, as a magnitude and an angle, right? I asked you to do it as a magnitude and an angle because I knew you would get the angle wrong, right? So rather than just saying it's -2, and you did, there's many questions in the chat, so it worked, right? So basically, what is this? This guy has a magnitude of 2. His magnitude is 2, and what's his angle? Yeah, it's
180.
180 or minus 180, right? So if you look at the way I wrote it, it basically tells you, most of the time I tell you go between minus 180 and 180. This guy I told you to go between 0 and 360, so that you would put in 180.
So this is just for one. And then did you also ask for V
So yeah, if I did for the other source, then I would have to go through the phasor analysis there. And I would have to say, well, at omega equal to 100 radians per second, what's the impedance of the capacitor? What's the impedance of the inductor? Those are not going to be open and short, right? They're going to be just impedances at that point.
I kind of had something similar having been used the 180, but I didn't understand it in problem one, like, because I think
In problem one, it was just resistors, right? And a DC voltage source. And that's tricky because there's nothing impedancy about that thing, right? It looks like a circuit from circuits one. But the fact that I have minus anything, technically phasors apply at any one frequency. Phasor analysis, impedance analysis always applies. The frequency in that case is DC in problem one. And I only have resistors, but I'm still basically doing, you were doing phasor analysis in circuits one and just didn't call it that, right? But technically it was the same thing, right? So you end up with a negative voltage. Negative voltage means that you have a voltage with an angle of 180, right?
But how do I know?
I mean, they didn't teach you that when, like in the 6th grade, when you learn negative numbers, they didn't tell you that -1 had an angle of 180, right? There's certain things we're always kind of keeping from you.
But how do I know if I need to add it or subtract it? My bounds, like what you're asking me needs to be between it?
Well, once I tell you in this case, I'm asking for the angle. If I give you just a negative real number like that, a negative real number has an angle of 180 or -180. The reason I said do between 0 and 360 is so that you wouldn't put in -180 and get marked wrong. Right. Most of the time, you're not going to have simple ones like this. Right. Most of the time, if it's a regular phasor problem, you're going to end up like -138.4 or something like that.
So the same concept would apply if you had two AC sources with different.
If I had two AC sources, same thing would apply if their frequencies were different. And that sounds like the ideal sort of thing for an exam problem, right? Yeah. I like that sigh.
At least there's no op amps.
There will be no op amps. That's right. Op amps will be op amps galore on exam 4. Okay.
Wait, so what can we expect to see on this test then?
I'll get to your question after. So, Mr. Fish, so I mentioned that at the very beginning. Basically, I'll rehash it one more time, which is that basically everything from exam 2 up until last week. So nodal analysis, mesh analysis, Thevenin, Norton, all that stuff with impedance, right? So if you look at the practice exam is it's really just practice problems that I put out there. They're all very similar to what I would expect to see. If you look at the homework, particularly homework 6 and homework 5, and I guess to some extent homework 4, which was just real basic kind of impedance stuff. Homework 5 and 6 are going to be the bread and butter of it. You know, I mean, you look at the problems, you probably get a pretty quick sense of what I'm going to do. There's going to be circuits where I tell you, you can't do nodal or mesh, right? And there's going to be circuits where there's dependent sources, and you probably have to do Thevenin and nodal, or Thevenin or Norton. So I think the practice exam problems give you a pretty good sense of what I would expect to be on there.
Professor?
Yeah.
So for this past exam, on the last problem, on the solutions, the solution was done in terms of milliamps. If we did it in amps, will we still get credit for it?
Yeah. I mean, I wouldn't, as long as you give me the right, as long as it's clear what the units are, that should be fine.
All right, thanks.
Yeah. No, I'm not going to be particular about units. The only time I would be particular is if and you'll see it in bold And if you look at the way exam 1 was, it was like in bold at the top of the problem. I think I made an announcement about it specifically to go with it. It will be crystal clear that I won't accept anything that way. Otherwise, I try to be pretty flexible. You may disagree with me, but I try to be pretty flexible. The number one thing that you will see probably in the grading of it is if it's clear to me that you don't understand the physics of the problem, that's when you start losing the points, right? Like if your KCLs are all wrong or your KVL is wrong, that's when it goes downhill. Okay.
Makes sense.
So yeah, I made the announcement the other day. Test 2 will be back on Monday. Okay. All right.
Professor, will you post the solutions to the practice exam?
We'll post at least partial solutions to the practice exam. I'll have office hours tonight if you guys wanna come and ask questions about it, about the homework or about the practice exam or life or whatever. I definitely have them tonight, 7:30 to 9. I'll see if I can squeeze some in tomorrow night, maybe.
So the practice exam says no nodal or mesh. Is that only for question 1 or it's for all of them?
So it would only apply to specific questions. I would never tell you that you can't do it on the entire exam.
Okay.
It would be on a question by question basis. Just like it was in exam 1.
How's this lab looking for? Like the lab,